then I can always write, and also I have another reference frame O prime, so this is Imad and Charlie. This is Imad. I can always decompose the electric field into two components, electric field parallel V and electric field perpendicular to V. Similarly for the magnetic field, so V cross E parallel is 0, V cross E parallel is 0, okay? And then the transformation, we derived it last Friday. This is what we saw, the parallel electric field transform simply, trivially, but not so for the perpendicular component. So there is a cross between E and V as given by this formula here. Okay, if you try to memorize it, I always forget the direction of the sign, right? But this is the formula. Just try to remember a little bit about it. Now, I just want to consider two special situations here, which is relevant for the next chapter. For in a special frame O, where the P field is 0, say if I just have a stationary proton, right? In the O frame, right? Then just plugging this into this formula, you'll see that that everything is trivial, right? So we know this parallel electric field is the same, perpendicular electric field, transverse electric field is enhanced by a factor of gamma. This we know already from chapter 5. But the B field that O prime sees is given by this formula here. Is the velocity across the electric field. There's no prime here, by the way. It's always too easy to make a mistake here because all the formula look the same. I mean, I keep on making mistakes in my notes and probably lecture notes too. So let's see. So combining all this formula here, I can always write gamma E perpendicular to be equal to E prime, right? And I can always write the whole magnetic field E prime as just the sum of beta prime, beta perpendicular plus beta parallel, but beta parallel is just 0. Then the prime magnetic field is given by just minus V cross.
Is that one prime also?
Yeah, this is also prime.
How?
This is all in the prime frame.
Okay.
But the idea is that if you know that O is moving at some velocity with respect to O prime at some velocity V, right? If you know the electric field, this is all measured by O prime, by the way. This is all measured by Charlie in this case. Charlie has become prime, okay? Right? So the B field, this is the E field seen by Charlie, this is the B field seen by Charlie also.
Okay, and the other one's the transformation, the one with the gamma?
This is, yeah. So I'm just condensing all this formula into something that's all observable and measurable in the O prime frame. Right? Okay, and we briefly mentioned an example with the field from a proton, but I don't want to go in that direction right now because there's a lot of algebra. But just remember that part. Okay. And just one more thing, though, right? As you see here, things doesn't have to be at a relativistic speed, right? Gamma can be close to 1 in this case. Right? If gamma is close to 1 with very low velocity, right? So, Charlie and Imad, that doesn't have to move very fast with respect to one another, right? This formula is still true, right? So in that case, right, this electric field E prime, if gamma is close, if beta is close to 0, then gamma is close to 1, and E prime is just close to E. Right?
Is the
But
B?
you still have a B field.
Yeah. Is that B field? Charlie is measuring one that's in the stationary frame. Is that from?
That's what Charlie's measured.
While he's moving.
If Imad sees an arbitrary E field and B field in space-time, right? except in this case here the B field is 0.
Mm-hmm.
And what Charlie sees is that
Right, but where is the B field? Like in whose frame? Is
this
it?
is in Charlie's frame. Everything is measured in Charlie's frame.
Which is the lab frame?
Which is, well, in this case, it's not, let's just
Yeah.
consider it free floating right now, right? We have to be able to go back and forth between lab frame and particle frame, right? Because in this case here, I'm considering the situation where, that the field is generated by you, by EMAT carrying parallel plates and solenoids and whatnot, right? Creating E field and P field, right? And Charlie pass by, and what does he see? Right? And this is what he sees. Right?
Okay, but the stationary frame sees 0? Is down there?
Yeah, stationary frame B is 0.
Yeah, in stationary frame B is 0. If B is 0 in the stationary frame, right?
Oh, we just
then-
said it
then-
this way?
Then the formula for the P field is very simple in Charlie's frame.
If you create a configuration that has 0 B field.
Yes.
Right?
Yeah.
In particular, say, if everything is at rest in EMAT's frame, right? So
Oh.
there is no B field generated. All the particles are at rest, no B field. Then Charlie zip through, and then this is what you will see, right? He doesn't
Because
have to
he's
go ahead-
moving?
Sorry?
Because he's moving?
Because
you
he's
see?
moving, right? Because he's moving, he sees this field, and we don't even have to talk about any relativistic velocity, right? This is, he sees an electric field, this is a B field. Okay. Similarly, the situation with the electric field is 0, right? Then you can go to the same thing. Just take that complicated formula over there and then plug it into plug E equal to 0 everywhere, right? And you'll find that the transformation is very simple, right? There's a B field transformation, and then I'm just writing everything in terms of the prime measurable, then E prime is just V cross B. Okay? And again, this doesn't have to be relativistic. Say if beta is equals to 0, gamma is equals to 1, and B prime is very close to P. Right? And then, so if you might measure B, Charlie would measure B also, approximately, right? But since Charlie is moving, he measures an electric field, that's just V cross B. Okay? So, with that in mind, let's consider the situation. Suppose I have a constant B field in that frame. B constant and is pointing in this direction. Let me actually consider this a simple case. So there's a B field like that, and I have a rod, right? And it moves in some velocity. Okay? So what happened here? What happened? One thing that I forgot to mention is this rod. This rod has length. This rod has length W, right? And it's actually made from conductor. Okay. So there's let's just consider all the mobile carriers. And for simplicity, the mobile carrier is positive, right? So the positive current move gives me positive I. Then in this case here, because you have a velocity in that direction, then you have a Lorentz force, right? And it's given by Q for a test charge Q here, right? One of the mobile carrier, Q V cross B, right? Is going to be equal to Q V B, and it's going to be in this direction, right? In the X minus Y. Okay, so this is going to be in the minus minus y direction. Okay. So what happened? Then this charge will move, right? It will move and migrate in that direction. Let me just draw it from the top view. So in this case, the B field is out of the board everywhere. Right? There is an F, and M here, right? Charge will migrate. So you have more positive charge here, right? And as a result, you have negative charges there, right? Okay? And then this will continue until you have enough built up of positive charge here and negative charge over there that it sets up an electric field that counteracts. So this charge built up, induce electric field that counteracts the magnetic force, right? When does that happen? Well, no, that's not considered yet. I don't want to calculate that for now. But basically what happens is there's an electric field, and the electric field perfectly balance the Lorentz force. Okay?
So this is initially this had
Yes.
initially it had a B field, and
Yeah, there is
then
a
the
B
conductor
field. So
started.
there is a B field generated in the lab. So maybe it's actually the Earth's B field, right? Except it's not strong enough. Well, it depends on the sensitivity of your measurement device, right? The Earth's B field, and then you have a rod moving in it,
Okay.
right? So it generated a Lorentz force, right? And then charge will migrate because it's a conductor, right? And then positive will be over here, negative will be over there, and they will set up an electric field inside the conducting rod,
Yeah.
right? In such a way that it will balance and counteract the magnetic force. And then when that happens, the build-up stop.
On the top-down
Yes.
diagram, what direction is V?
Is outward. From now on, this is a standard practice. This is outward.
No, V, not B.
Oh, V is
Yeah.
yes, V is in this direction.
Oh, okay, so in the side picture, the rod is moving towards us directly.
Yeah, I'm always very bad at drawing this right. This rod is going that way. I'm just drawing it.
If it's V plus V.
Right. It's ugly. Right?
But where is B?
Basically, I have a rod
V's up.
Yeah.
moving like that.
It is a label, so I should just draw in a V.
See, I'm drawing.
The V feels
My
the lines
drawing
down.
is always awful.
Okay.
And then
Oh,
That's why
those upward lines.
yeah,
are B.
that's the B's in the Z direction. And then
Do you mean you just have like a neutral
So, how do
conductor
you know?
and you use that in magnetic field?
Yes.
Oh.
Polarize it.
Okay.
It will polarize it,
Is this the way?
and then the polarization will create a counteracting
force.
electric
Okay,
field
forces
that
are
balance that force. And when that happens, the build-up stop. Right? Okay. And let's not calculate the exact how much the build-up and everything. We could do that, but it's very complicated for now. Just to finish this, every time I draw this is B field in the board. Okay. But what does say Charlie say is with the rod, right? Charlie is with the rod, then it's stationary, right? But what does he see? This is a special frame, in the image frame, right? In the lab frame, the electric field is 0, right? There's only B field, right? So in Charlie's frame, in the frame of the moving rod, then the electric field is given by V cross B, right? So if I look at it, V is out of the board. No, V is that way. Cross B, which is out of the board, gives me an electric field in this direction, right? So here in this frame, according to Charlie, there is an electric field E prime everywhere that's equal to Vx Vz, and is in the minus y direction. Everywhere.
It does that with the B field or it does that with force?
Charlie.
So So,
O prime, right?
which is the
O prime is the moving together with the rod, right? Sitting on the rod, right? Sitting on the rod and moving like that, right? And you will see everywhere, because everywhere there is a B field everywhere, like that, right?
Yeah.
And by this formula, because there's a B field everywhere, there is an E field everywhere. And E field is given by V cross B. Okay?
So the B field for him, does it disappear? Like, does he not see the B field?
He also sees the B field.
He also
but
sees the B field.
There is also a
Right.
B field, but I don't care about the B field. In this case, I don't really care about the B field because the rod is stationary.
Oh,
Right? Okay? So there's a B field. Incidentally, there's a B field, but yeah. Okay?
Are
So-
the lines the B field or like
Sorry?
velocity? The lines?
The line is the
Alright.
E field.
E. Oh, okay.
Right?
Were
it's
the
not
lines
considered
up there also the E
field is
field?
still the B field is still outward, but it's a different magnitude.
Okay.
Right? There is a B field outward,
Wait, how did you?
but it's changing magnitude.
What is stationary again?
Sorry?
The rod.
The rod is stationary in this case. Right?
And up there, the lines pointing upward were also the E field?
That's the B field.
Okay.
Right? That's the B field. Okay. That's the B field going. That's a 3D picture, right? Here in this case, let's just consider this picture. Right? There's a B field outward everywhere. Right? Out of the board.
Oh,
And
you
there's a rod
oriented
moving
it.
like that. Right? So this is the Z direction.
Oh, he moved it,
X.
that's why. Okay.
X, Y, and Z is out of the board. Right?
Mhm.
So what happened when I jumped into the frame, when Charlie jumped into the frame with on the rods, they are sitting over there, and this is stationary, then he sees an electric field everywhere like this. Right? And it's given by this formula. V cross B, right? Which is just that, right? PC prime, by the way. But I'm a bit cavalier about the magnitude of PC because in this case the rod doesn't have to move very fast. This can happen in the lab, right? Gamma can be close to 1. In that case, PZ prime is just equal to PC.
I'm a little confused. So in the formula you gave over there, you said that it's in a special frame where in the lab frame E is 0.
Yes, yes.
But did you just say that there was an induced E field because of?
Afterwards.
Oh.
Yeah, I mean, then you, of course, yeah, that's why I said that the discussion on how much build up is actually pretty complicated, and I don't want to go into that. That's a second order effect. Okay? Initially, there is some other source that's much stronger that's producing a constant B field. Right? And then in Charlie's frame, suddenly he sees E field everywhere. Right? So what happened here, this is a conductor, there's an E field. Right? So you will polarize this because in a conductor, E field has to be 0. So what happened because of the electric field, you will also have charge build up. Right? You better see the same charge because of the relativistic invariance of charge. Right? And E
yeah.
field is 0 in here. Inside the conductor, as usual, right? It's a conductor, stationary is the simplest thing, right? So E field has to be 0. Right? So what happened is that you start to see something like this. Right? And you see something like that. Remember, on a conductor, everything has to be normal, right? Electric field has to be normal. The surface of a conductor. So you start to see something like that. The conductor will just change the configuration of the electric field. Okay. And back to the question that Nicholas asked, and after all said and done, if you maybe you can do it on a computer, then the field transformation here and there should agree with one another.
Why did it go outward, not
Oh.
down?
Oh, because the field is everywhere like that, right? So you will polarize it. Right? There will be plus charges, or the plus charges will move to this side, right? And minus charges will move to that side. But there is a constant E field going this way. I'm just doing the boundary, doing the continuing, like just continuation of this flow of electric field, and I have a boundary deviation. convention, just drawing it
Okay.
as such. Okay, question so far? Okay. So that's what happened, right?
I have a question.
Yes, okay.
In Ahmad's frame, in the conductor, he doesn't see electric field being zero.
In Imad's frame, Imad is stationary with the lab. He sees an electric field inside,
Exactly.
because of the polarization, right? First you see a Lorentz force, right? The charges will build up at the end of the rods, right? At both ends of the rod, and then that will set up an electric field, right?
Inside the conductor?
Yes, that I'm not considering, right? Inside the conductor, at the end of the day, you have a steady state solution, right?
Yeah.
Stationary, because after a while, you polarize the conductor, and then nothing will move anymore,
Right.
right? So then you set up an electric field inside also, right? There is a Lorentz force that polarizes the conductor, right? And then that polarization creates an electric field that balances it.
So does the rule that E has to be zero inside the conductor not apply when the conductor is moving?
Yeah, that sounds good.
No, it's never like that, right? If you have a, it's a very good question, because in this case there is no steady state of current, right? Yes, that's actually probably a good question that I'll get back to you on that. Otherwise I'll get lost in the thought and then not. But yes, it's not it's definitely a steady static case already, but there is an electric field set up. Right?
Inside the conductor.
Inside the conductor. Right? Yes,
That's so weird.
So let's move on and consider the following case. Now that we have enough machinery to understand everything now, including Faraday's law, right? And that will be the next 2 lectures basically. So if I have a B field everywhere out of the board, right, and I set up a loop, right, a stationary loop, or a U-shaped thing, right? And I put a rod here. And I give it, this is a conductor. Everything is a conductor. Okay? I give it some velocity v in that direction. Right? Then if I consider, well, of course, you now know that there is this part here from A to B, right? If I consider an integral, there is a Lorentz force here B and B. There is a Lorentz force given by Q, B, B, right? And it's going to be in this direction. Okay. Let me consider the force per unit charge, F. And per unit charge, and this is equal to just Q minus V in the minus Y direction. Now, let me consider this integral here. Except that I'm doing it in the opposite direction, right? Sure. Let's just consider, let's consider the integral, but this is actually going this direction. Let's call this A, B, C, D, right? And the integral goes in that direction. Of F, okay. This is going to be equal to the work. I'm confused with the sign, right? Because I just want to make sure that this is actually transparent. Let's consider a P field. Let me just go through my notes. Let's forget about the sign for now, right? Let's keep on doing this. A, B, C, D. And let's consider a closed loop integral from A, B, C, D of F theta. Right? Okay. So this is equal to the work done per unit charge by the B, right? because there's a magnetic force, right? And all along the wire, in particular, just considering in this segment only, because this is the only place where you have movement, right? And that's the work that the magnetic field is doing. And I'll talk more about that later. And this is called defined as the EMF, the electromotive force. Okay. And in this case here, because it's zero everywhere, this is just equal to, because on the rest of the segment, nothing is moving, this is just equal to V times W. The W is the width of the rod. Okay. Okay. And when that happens, you have current generated. Because charges will move here. In this case, there is no build-up of electric field, by the way, right? Because the Lorentz force move the charges, right? Then you have current. Right? And if this thing has a resistance R, right, then current will be equal to just an analog, exactly with chapter 4. In fact, we will get a situation where you have a battery. Sometimes it's called also electromotive force, right? R. Right? Here, I is just the EMF. Right? So current will flow. Okay. Clear so far?
In that diagram, why does the current go counterclockwise and not clockwise? Because from like the previous diagrams,
Yes. No, current will actually go. I'm just defining direction here. I'm being cavalier with the sign because I don't know where to put the right sign, but I'll put it in the right place at the end of the day, right? But I'm defining. I want to make sure that I define at least set up the problem in such a way that I follow the right hand rule, right? So the electromotive force is defined as a line integral of the Lorentz force, right? So that follow the right hand rule in this case here. I want to define it so that this is positive circulation, then give you a peak going outward that way. Okay? And then I'll take care of the sign later on. Okay? So that's the direction of the current. And if I look at the this expression for the EMF, right? Let me rewrite it. VW, right? Let me consider this situation, right? At time t, this is W, and this is moving at some velocity V. At later time, this will be over here, right? This is at time t, this is at time t plus delta t. Okay? Now, if I multiply V, W, V times t, right? Suppose this is t equal to 0, the rod is over here at t equal to 0, right? Then this is just the flux through the loop at t, right? Because this is just equal to t times the area. Okay. And then the flux at times t plus delta t is given by d omega v times t plus delta t. Okay. There is a flux through this loop, right? And as I increase I move the position of the rod to the right, there is an increase in the flux. right? And the increase in the flux, delta P, then it's just the difference between these two. It's just then this just becomes equal to B omega P delta T. Right? Now, as you see, then the EMF, right? Let me just rewrite that equation in the limit of delta t equals to 0, right? Then delta t becomes dV dt, that becomes just dW, right? This is the change in the flux through that loop for a stationary magnetic field moving with of a loop moving in a stationary magnetic field. Flux change. Okay, and this is another problem with the sign. I did my sign. Okay. But in this case here, the change in flux is positive, right? Because as I change the rod to the right, I increase the flux through that loop, right? But the current actually, the EMF actually goes the other way, right? So EMF then, if you look at the expression for EMF, it is the same here. I'm just considering the magnitude. This is going to be equal to minus. It's clear. I probably just mangled the whole thing with the sign for whatever reason I couldn't place it. But this is the right formula, right? The increase in the flux causes an electromotive force going in the opposite direction. Okay? And this is for loop moving in stationary field. Okay? You can generalize that statement, it turns out, and I will go through that. You should just follow the discussion itself, right? Here, I consider an artificial, a very simple case where I have a square loop moving perpendicular to a stationary magnetic field. But you can generalize any loop, any shape, moving in any velocity. Meaning that the loop can also change its shape, right? It can breathe in and out, say, right? But in a stationary field, the proof is not that hard, but it has factor algebra, and I know from the previous few lectures, factor algebra is going to be confusing. But if you read it yourself, you'll find that formula is still true. EMF generated, or E, is given by the change in the flux through the loop as a function of time, right? Okay. Now,
Can you clarify what stationary B field would mean? Like, is it your...
meaning that if I create a stationary B field in the lab, right?
In the lab frame.
In the lab frame, right? So I'm now always in the lab frame from at least for now, right? So the B field generated by the Earth, right? And I have a loop moving through, right? And as it moves through the lab, it sees a change in B field, right? It sees a change in flux, right? And when it sees a change in flux, it creates an induced electromotive force
Oh.
in that loop, and it's given by this.
So by stationary, you mean kind of constant B
Sorry?
field? Like by stationary, is it just?
No, if the B field is always, if the B field is constant, or without any spatial variations, say, right, then the loop always sees the same flux, then there is no EMF.
So what do you mean by stationary?
Meaning that the B field doesn't change in time. Independent of time. It's not changing in time. But it can have variation spatially. It can be strong here and weaker here. Right? So if I consider a loop, so if I B field everywhere, right? And then I have a loop, moving like that, right? You can calculate the same thing. You don't have to go through this machinery of calculating flux. You can just go through the calculation of the Lorentz force. You see the Lorentz force on this side will exactly balance the Lorentz force on that side, right? Give you a 0, and then it will give you 0 EMF. Right? Because you have VPW on one side minus VPW on the other side of V1 is equal to V2, and this is equal to 0. Right? But if somehow the B field here is stronger, if V1 is larger than V2, larger than V3, say, and so on, right? Then the Lorentz force here is stronger than the Lorentz force there, right? So as you move, you lose more fluxes from on the left side than you gain on the right side, right?
Yeah.
And then you have changes in the flux.
So it's when there's like discrepancies in the B field, like just change. It's
If
different. It's not.
the B field is spatially varying in
Yeah.
space, but stationary in time, right? It doesn't change with time, but it varies in space, right? Just like a landscape, right? And then if I move my loop through it, I will get an EMF.
Okay. But not if it's like flat or if it's the same.
Yeah, but if the B field is constant everywhere, then as I move the loop,
It doesn't.
it doesn't create an EMF because the Lorentz force on opposite side of the loop balance one another. Okay. Question on this? What did I say? I said that if the B field is constant everywhere, right? Then if I have a loop moving through it, then in this case, say a square loop, then the flux that you lose, say on the left side of the loop, will exactly counteract, will exactly be balanced by the flux that you gain on the right hand side of the loop, right? So the change in the flux is 0, and then you have 0 EMF. Is that clear? Okay. And go through the proof. There's a lot of vector algebra in the proof. I'm just considering a simple loop here, but this is actually a general statement. Any loop, any shape, any movement. Okay.
And can the velocity be varying the same way the shape could be varying in time?
Yeah, so in that case, then if your loop is breathing like that, right, your loop is like this here, right? C
Right.
at time t, and at time,
Right.
at time t plus delta t, it's like that, right? So different part of the loop has different velocity,
Yeah.
right? Right. But at the end of the day, all you need to do is find the flux to this loop and find the flux to that loop. Take the difference. That would be the line integral of the Lorentz force over the whole loop, which is the EMF.
Is there only an EMF induced if you have a conductor or something in there? Like you can't if you just imagine like an imaginary conductor moving.
Yes. Well, there is an EMF there, but that's a lot of discussion. I mean, you only have a force if you have a particle moving in it, right? So in this case, there is a magnetic field, right? If you have an imaginary rod, then it doesn't create any force, you see what I'm saying? But you have the B field and you have the E field, right? And the B field and E field transformation is still the same, right? But you're right, the consideration of the EMF here requires that you have something physical, right? But later on, you generalize from that. See, I haven't mentioned Faraday's law yet, right? I haven't said anything about Faraday. Right? I just talked about moving rod in a magnetic field. Okay?
Just back to this example with the different B fields. In the case where like it's greater on one side, I mean, like which side is greater than one and the other as it moves through this like gradient?
Oh, so the B field is strong on the left and is weak on the right.
Okay.
Right? So the loop is moving that.
Okay.
Right? So in this case here, as it moves, right, the amount of flux that it loses on the left is more than the amount of fluxes that it gains on the right. Right? Because the field is always stronger on the left than on the right. So there is a change in flux. Right? And then that will give you an EMF.
What if don't have a stationary B field, like it's a constant one, but
Yes.
your velocity
Right, the B fields are all the same.
but you're like accelerating through it, or
Yeah, you're moving at some velocity B.
if your velocity is changing.
Uh,
I think that's kind of what he asked.
Yes,
but
yes. If
I remember.
nothing is relativistic, then yeah, if the velocity can be changing, right, it's fine. You get
You still
the
get EMF.
EMF is still given by the change, the rate of change of the flux.
Mm-hmm.
Right? The loop can be of any size, any shape, moving with any velocity, and it can breathe in and out, right? You just calculate the flux through it, calculate how much it changes in time, take the derivative, and that is your EMF. That will be the circulation of the magnetic force over the loop, right? And then if your wire has resistance R, then it will create a current that's proportional to EMF divided by the resistors. Okay? So for the next 5 minutes, I want to mention a way to memorize the direction, right? There is a minus sign here, right? And so we have to be very careful. There's a mnemonic for it. In fact, it's named after a person. It's called the Lenz law. Right? So if I move through a B field, like this is my loop, right? This is again a 3D drawing, right? X, Y, Z, B, right? It moves through a varying magnetic field, so there is a flux change, right? So there is a and this will give you EMF, right? Question is the direction. Right? The direction is always such that so let's see. Suppose let's talk about the example. Right? Suppose the B field is decreasing, right? So 1 and 2. Right? So as I move in that direction, then the flux goes down, right? The flux goes down. And the direction of EMF is such, this is Lenz law, just a way to remember, right? The physics, we already finished the physics. That the direction of the EMF is such that it will create, so the sense of the EMF is such that the induced current created will counteract that flux change, right? So in this case here, there will be an induced current I like this, right? And remember, if I have a loop, here, this is, you have to remember from our discussion of Biot-Savart law, if I have a loop like this, the current going that way, right? Then there's a DC in that direction, right? So in this case here, the direction of the EMF is such that the induced current created will will try to add that magnetic field in there. Because it sees a diminishing magnetic field, right? It sees a diminishing flux. And it wants to counteract that. Right? It does that by creating a current, right, that will increase the P field through that loop. That's Lenz's law. Right?
Like, the current is created because it's a
That's
reduced
the EMF,
EMF?
right? Because of
Wait.
the EMF. Right? The loop has a resistance, the EMF is like the voltage,
Yeah.
so it creates a current, right? And the current creates a direct, this is just the top of direction, right? Because, I mean, I'm not the only one confused with the sign, right? But there is no ambiguity if you divide everything correctly. But this is just a way to remember, right? That there is a negative sign here, right? Mathematically, but physically, this is what happened, right? The loop sees a diminishing magnetic field, right? It will create a current, and the current created is created in such a way that will actually increase the flux through that loop to counteract for the diminishing flux.
And so basically, just from the formula, then it's negative d phi dt, and then
Yeah,
but d phi dt is negative because the flux is going down.
Yes,
And
yes.
so the negatives cancel, you get positive, and that's the physical reason.
Correct, correct. Well, this is just a way to remember it, right? But here the negative sign is just making sure that this is the loop, right?
Yeah.
If this is the direction of the flux, this is positive direction of flux, then this is positive direction of EMF. Right? So always remember in a discussion of magnetic field is not a polar vector, it's an axial vector. So you always have to remember this rule, right hand rule. Right? And in this case here, of course B field, flux is due to B field, and it's going that way. Then EMF has to have this sense. Positive sense follows the right hand rule. And the minus sign has to keep you well, it has to move the other way.
This B field that's created from the current, does it increase as it goes to the right, as it moves? As the B field gets smaller?
Yes, I'm not doing calculation here, I'm just doing mnemonic here, right?
Yeah.
So for you to remember it, right? But it's actually, there's a name for it, it's called Lenz's law, right? Yeah, but basically B field is diminishing as this will move to the right. Induce a current that try to counteract that, right? And that will create a B field of its own, right? And I stopped the analysis there because you can do a regression, right? Because it creates another B field, and then create another induced EMF, and the story goes on. But eventually it actually converges.
If that B field creates another EMF? That's
Yes, right. And we'll talk about that later on. There's what's concept called self-inductance. Right? That's how an inductor works. Okay. So just to clarify, this is not yet Faraday's law. Right? This is not Faraday's law. Right? That's actually the subject for Wednesday. I mean, it looks similar. If you have done this in high school, it looks similar. Right? But here we have a stationary magnetic field, a moving loop. Right? Faraday's law is a more generalized concept than that.
By the way, I think I just got